Okay, so when we talk about single degree of freedom systems, I would like to set an example here with a one-story floor system that is supported by columns. Typically, this is the setup for most of our buildings here. Our structures are composed of beams, those that support lateral gravity loads. Also, the columns support that will resist axial loads that are generated from the beams, the columns, and it is then transmitted to the floors. Now, what we will study here is how the building behaves when it is subjected to a lateral load that is generated from seismic activity. This is what we call the FT, which will be termed as our forcing function. Forcing function, or the seismic generated load, or the seismic load, seismic lateral load, and this is our structure here. Now, our structure also possesses mass. Now, this mass constitute from the objects that is being subjected, the structure is being subjected to, which will be converted to mass. Also, it is supported by columns. I'll just write down this. Now, the columns, inherently, they have also what we call as the stiffness, or what we will observe as the ability of a structure that can resist motion, that is stiffness. Now, these columns possess K, stiffness. I'll just generalize this as the K of the structure. So this is what we call as the structural stiffness. Now, what exactly happens when an earthquake occurs? Now, the lateral load that is generated from a seismic activity, when it manifests itself in the structure here, this will tend to go sidesway, move like this. So this, let's write this down. That way will become will move this direction. Okay, can also move upwards, but then let's just start with the simple basic principles lang. Okay, so this movement here is what I said earlier to be defined as X, which is our story drift, or for generalization purposes, just call this as the displacement. I just call this displacement because we will be talking about differential equations. So I think this is a much more appropriate term. Okay. So anyway, when we have this, we cannot analyze this figure directly, no? So I find it much cumbersome. So I would like to somehow revamp this into a more easier interpretation of things. I would like to use this as remodel this as a lump mass model. Okay. Sorry if there are a lot of technical difficulties here. I'm still getting used to the online learning gig. So this is the okay. Lumped mass model. Now, what we would like to do with the lumped mass model is that we will try to convert this structure here into a more simple, mas dali siya ma-analyze o silbi na object. Okay? So, what I would like to do here is that I will create an equivalent system, but basically, the same principle lang siya. Have this. Okay? It still has the same stiffness, K, and also still subjected to the same seismic load, which is defined as Ft. Okay? It still contains the same mass and basically has the same properties. Okay? The mass here, in here, is already been generalized and it is being lumped, thus the term lumped mass model. Now, when this seismic activity occurs, this structure deflects in a way is almost similar to this. In which the displacement will still be called as x. Okay? So, I think the lumped mass model is a much more appropriate way of presenting things rather than the actual figure here given. Okay? So, I'll just pause this video and then, okay. Talking about the lumped mass model, it still retains the stiffness K, the original structure, and also the displacement, as well as the forcing function known as the seismic load. Now, other than that, there are also properties to the structure that is inherent here. Now, our structure possesses mass. There's what we call the personality, or rather the characteristic of mass that somehow resists motion. That is what we call the inertia. So when we say inertia, that is the property of a material that can resist that resists motion. Now, this can be placed here as a damping. It be rather represented here as a damping force. Now, force of damping. Rather, I think this is a much more appropriate purpose. Force that is inertia. Okay? This is motion. Other than that, what else is resisting motion here is also the inherent stiffness of the columns. So, you can also find it here, that stiffness, or shall we say K, so our stiffness here. Now, not the inertial, rather. This is the damping force. Now, the lump mass model can also be further simplified into a more tangible equivalent. Now, I would like to write down here the equivalent model. Which is can be similar to a small car. Okay, placed here are two wheels, still retaining the same mass, but it has. Let's try to place the stiffness here. Try to incorporate the stiffness here, which is Fk. Aside from that, we have the damping force, which is equal to Fd. And of course, we still have the forcing function here, which is equal to Ft. Okay, so this is the equivalent model. Now, I'd like to write this down here. I'd like to erase this. Seismic load, mass, stiffness, displacement. And write down that Fd is our force due to damping. Damping. Now, when we talk about damping, it is actually what it is the ability of a material that to dissipate kinetic energy. Now, when we're talking about earthquakes, there is a release, a sudden release of kinetic energy. Now, kani siyang damping, eventually, muna siya kanang murag mo, paspas kang liyok ano niya, and eventually hinahinay na siya dissipate ng kinetic energy niya, muhinay na lang din siya. Okay? So, from fast movement until to slower, until murag back to at rest na dayon. So, muna siyang ibig sabihin sa ito ang force, talk about damping. That is the property sa material na may na siya. Now, talk about stiffness pod. That is a different na sa na kuan. Talk about energy. This is the inherent spring stiffness lugar silbi spring. Let's try to label that Fk as a spring system kay when we're talking about the stiffness sa tuhang kuan din sa tuhang mga columns. Now, Fk, that is defined as the force due to stiffness. Okay? In a way, both these forces, ngayong tanawon, gina-resist niya ang movement na gi-induce earthquake. Okay? So, from there, still the forcing function. Now, napunto siyang inertial force din dito ganiya. Now, this will come out later na dayon when we say FBD. From this equivalent model, we try to analyze this sa FBD, force free body diagram from our mechanics. Now, free body diagram, FBD. I take this car here and I bring out the forces dapat ma-reflect siya. Okay? So, this is our forcing function Ft. Our Fd damping is resist na niya ang klaseng movement. Another Fk is also resisting movement sa yaha. Okay? This is our free body diagram. Now, aside from that, I would like to find another equivalent for this that will end up yung resultant silbi. I just call this MAD. Okay, I'm not mad, so MAD stands for mass acceleration diagram. Okay? Mass acceleration diagram. Now, all of these forces should coincide and should result to this. Still having our mass here, but ang yang ko na niya, resultant ng gidan silbi dayon is that in the end, it will still move this way. Okay? So, mass times acceleration. Okay? Now, let's try to relate these terms displacement, velocity, and of course, terms for much more mas dali siya madula-dula. Mathematical terms rather. Now, if x is our displacement, can't be seen displacement, okay? Its first derivative is actually called the velocity, and the second derivative is our acceleration. from calculus. So let's just place it here, and then we will I'll just make more room for this, then we discuss further.